Hello friends, welcome to this video. In this video, I'm going to talk about rank of a matrix, some of its properties, and we'll see how we can apply these properties on some of the previous year problems of JAM. So let's start with the concept of linear independence. Let V be a finite dimensional vector space of dimension n over real numbers. Let's take any m vectors v1, v2, vm in V. A linear combination of these vectors is an expression of the form c1 v1 plus c2 v2 plus dot 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 cm vm, where ci's are real numbers. So basically we multiply each vector by some scalar, some real numbers, and we add them. This combination is called linear combination of vectors v1, v2, vm. We say that vectors v1, v2, vm in V are linearly independent if there is a unique way to obtain zero vector by their linear combination. Of course, if you multiply each vector by 0 and add them, you'll get the zero vector. And there shouldn't be any other way to combine these vectors and get 0. Then these vectors are linearly independent. In other words, we can say that if c1 v1 plus c2 v2 plus cm vm is the zero vector, then all these constants c1, c2, the cm, they all should be 0. If this doesn't happen, you can find non-zero constant c1, c2, cm such that c1 v1 plus c2 v2 plus cm vm is 0 for at least one non-zero constant ci, then these vectors are called linearly dependent. Let's understand this using an example. Let V equal to P3x be the vector space of all polynomials in X with real coefficients and of degree less than equal to 3. So probably you have seen this vector space. It has dimension 4 and one basis of this vector space is 1x, x squared and x cube. Okay, in this vector space we take three polynomials x, x square minus 1 and x cube plus 3. Now we want to check if they are linearly independent or not. So we set the equation c1 times x plus c2 times the second polynomial x square minus 1 plus c3 times the third polynomial x cube plus 3 equal to 0. And now we can write them by combining the coefficients c3x cube plus c2x square plus c1x, and the constant term becomes 3c3 minus c2 equal to 0. Now this is a polynomial which is identically equal to 0. So then all the coefficients must be 0, which gives us c3 must be 0, c2 must be 0, and c1 must be 0. And getting this linear combination equal to 0, giving us that coefficients must be 0, these polynomials are linearly independent in this vector space. Let's see another example. This time we are in the vector space R4 and we are considering these three vectors v1, v2 and v3 in R4. Now we can see that 6 times v1 minus half times v2 minus v3 will be the zero vector, that is 0, 0, 0, 0. Just to verify, check the first coefficient. 6 times 3 minus half times in v2 the first coefficient is minus 6 minus in v3 the first component is 21, and this will be 18 plus 3 minus 21, and it's turning out to be 0. And you can check for other components as well that you will get 0. And so we got non-zero numbers c1, c2, c3 which combine to give the zero vector, and hence these vectors are linearly dependent. Okay, so with concept of linearly independence in our hand, we are ready to define rank of a matrix. So suppose A is a m cross n matrix, that is A has m rows and n columns. Now rows of A are vectors in Rn, while columns are vectors in Rm. So let R1, R2, Rm be m rows and C1, C2, Cn be n columns of A. then the maximum number of linearly independent rows which you can choose from Ri's is called row rank of A. So R1, R2, Rm are all vectors in Rn. Probably they are all not linearly independent. So what is the maximum number of rows which you can take out of these m rows which will be linearly independent, and that maximum number is called row rank. Similarly, you can talk about columns, and the maximum number of linearly independent columns which you can choose out of Ci's is called the column rank of A. And then we have a very interesting fact which says that for any matrix A, row rank is always equal to column rank. And so we just call it rank of A and we'll denote it by rank A. Okay, so let's understand the concept of rank by an example. So we take this matrix as an example, which is a 2 cross 3 matrix. It has two rows and both rows are vectors in R3. We denote them by R1 and R2. It has three columns which are vectors in R2 and we denote them by C1, C2 and C3. Now let's look at the rows, and you can easily see that R1 is nothing but minus 2 times R2. It means both rows are not linearly independent and only one of them is independent, because of course they are non-zero vectors. So row rank is 1. Similarly, if you look at the columns, you can write C1 as minus half of C2, C2 as minus 2/3 of C3 and C3 as 3 times C1. What does it say? That none of these columns are pairwise linearly independent. So the column rank is also 1 because these are non-zero column vectors. So the rank will be definitely at least 1. So row rank and column rank are same, and our rank of the matrix is also equal to 1. Okay, so after understanding the definition of the rank, let's look at some properties of rank. So first property of rank is that the rank of a matrix is 0 if and only if the matrix we have is zero matrix. Zero matrix is a matrix in which all entries are 0. So if you have a matrix in which at least one entry is non-zero, then it will have at least rank 1. The second property of rank is that rank of A is less than equal to minimum of m comma n, where m is number of rows in A and n is number of columns. And you can see why that is true, because we just saw that rank is equal to row rank as well as column rank. But since matrix has m rows, its row rank can't exceed m. Similarly, the matrix has n columns, so its column rank can't exceed n, and hence rank of matrix is always less than equal to minimum of these two numbers. If the rank of the matrix is equal to the minimum of m comma n, then we say that the matrix have full rank. Okay, so next property is about product of matrices. So let's say A is m cross n matrix and B be n cross k matrix, then AB is a m cross k matrix, and rank of AB will be less than equal to minimum of rank of A and rank of B. And also the equality will be achieved if any of A or B is of full rank. So now what can we say about the rank of sum? So of course we can add two matrices only when their dimensions are same. So let's say A and B are two m cross n matrices, then rank of A plus B is always less than equal to rank of A plus rank of B. Now the last property which we'll talk about is that let T V to W be a linear transformation where V and W are finite dimensional vector spaces. Now T can be represented by many matrices depending on what basis we choose for V. So there are many matrices representing T. But the interesting fact is that ranks of all these matrices representing T are same, and that's what we call rank of T. So rank of T denoted by rank T is the rank of any matrix which represents this linear transformation T. Okay, so let's try to solve some problems using concepts we just learned. So in this problem, it says that P is a 4 cross 6 matrix and Q is a 5 cross 4 matrix. Okay, and rank of Q is given as 4. Now see that since Q is 5 cross 4, rank of Q is 4, this implies that Q has full rank. Okay, it's a full rank matrix. Great. And now it says that if rank of QP is equal to 2, then we have to find what is rank of P. Okay, so now rank of QP, we know that is less than equal to minimum of rank Q and rank P, but we also know that if one of Q and P is a full rank, then the equality is achieved. So rank of QP is either equal to rank of Q or rank of P, because Q has full rank. Okay, but it is given to be equal to 2. Now we know that rank of Q is 4, so it can't be equal to rank of Q, right? So rank of QP has to be equal to rank of P, and since rank of Q is given to be 2, we know that rank of P is also equal to 2. Okay, so this next problem came in JAM 2017. Here P is a 7 cross 7 matrix and it's given that rank of P is equal to 4. Okay, and A is a column vector in R7. So it says that what is the least rank of P plus A into A transpose. Okay, so if you remember, we have this inequality that rank of sum of two matrices A plus B is less than equal to rank of A plus rank of B. But what this inequality does, that it gives you a upper bound on rank of A plus B, right? It's bounding from above. But what we need here is a lower bound on rank of A plus B. So how can we change this so that we get a lower rank? So what we do here is, since we need a lower rank, how about we choose A to be P plus A transpose, and we choose B to be minus A into A transpose in this inequality. And this should still hold because it holds true for any matrices A and B which you can add. So then rank of A plus B would be equal to rank of P, okay, and that would be less than equal to rank of A, which is rank of P plus A into A transpose, plus rank of minus A into A transpose, right? And so now rank of P is given to be 4, so this becomes 4, and rank of minus of A transpose is same as rank of A into A transpose, right? Because a matrix A and its negative will have the same rank. So this gives us that rank of P plus A into A transpose, which is this side, will be greater than equal to 4 minus rank of A into A transpose, right? So we want at least now what will be the rank of A into A transpose. So this is something which you should know, is that if A is a column vector, right? So A is 7 cross 1 matrix, right? And then A transpose is 1 cross 7. So A transpose is a 7 cross 7 matrix. So whenever you construct a matrix like this from a column vector, its rank will be 1 unless the vector you have chosen is the 0 vector. Okay, this is always true. Okay, so this matrix here has rank 1, so this is equal to 4 minus 1 equal to 3. So rank of P plus A into A transpose will definitely be greater than equal to 3. Okay, so this question is about rank of a linear transformation which came in 2018. So the linear transformation T is defined on vector space of polynomials of degree less than equal to 3. So we know that this is a 4-dimensional vector space and a basis for V is 1 x, x square and x cube. So T is a map from 4-dimensional vector space to 4-dimensional vector space. So if you represent T in a matrix, it will be a 4 cross 4 matrix. So let's find the matrix representation of T with respect to this standard basis. So what is T of 1? Polynomial 1. It will be 1 minus derivative of 1 will be 0. So it is just 1. What is T of x? It is x minus x times derivative of x, which is 1. So x minus x, so it is 0. What is T of x square? It is x square minus x into derivative of x square is 2x, so minus 2x square. So this is minus x square. And what is Tx cube? It is x cube minus x times derivative of x cube, which is 3x square. So this is 3x cube. So this is minus 2x cube. Now T of 1 is going to 1. So the first column will be 1, 0, 0, 0. Right? Now Tx is going to 0. So then second column will be 0, 0, 0, 0. Now T of x square is going to minus x square. It means the third column would be 0. There is nothing with respect to constant. Then a coefficient of x is also 0. Coefficient of x square is minus 1. Then 0. Coefficient of x cube is 0. And then Tx cube is going to minus 2x cube. So no constant coefficient, no x coefficient, no x square coefficient, only x cube which has coefficient minus 2. So this is the matrix representation you got. Now you can easily see that one column is completely 0, so rank is 3 or less, but then these three vectors are definitely linearly independent from each other because they have non-zero entries at different places. Okay, so there are three linearly independent columns, and so rank is 3. Okay, so this next question also came in JAM 2018, and here m and n are natural numbers. M is given to be strictly less than n, so this is important. P is a n cross m matrix, Q is a m cross n matrix. Then we have to tell that which of these statements are not possible. Okay, so first statement is about rank of PQ. Okay, so we'll use our inequality. Rank of PQ will be less than equal to minimum of rank P and rank Q. Okay, so since P is a n cross m matrix, its rank can't exceed m, right? M is strictly less than n, so it can't exceed m. Similarly, Q is a m cross n matrix, so again its rank can't exceed m. So since both these ranks can't exceed m, rank of PQ also can't exceed m. The same logic, because the same inequality is true, goes for rank QP. Both of them should be less than or equal to m. So this is possible, but since capital N is strictly greater than m, this is not possible. Rank of PQ can't be equal to n because it's a number bigger than m. Okay, now what about the third one? This says that rank of QP is m plus n over 2 ceiling, which is the smallest integer larger than or equal to m plus n over 2. Okay, so it's larger than or equal to m plus n over 2. So here m plus n over 2 is larger than or equal to m plus n over 2. Okay, which we can write as m over 2 plus n over 2, right? And remember that m is strictly less than n, so this is so this would be greater than m over 2 plus m over 2, strictly greater than, because n is strictly greater than m, so I replaced n by m. This is m. So basically this number is strictly greater than little m. And so again, since rank of QP has to be less than equal to m, it can't be this number because this number is strictly greater than m. So 1 and 4 are not possible. Okay, so with this, we are done with this video, and thank you for watching. Thank you very much.